Hello, welcome to the 19th topic in this course. We're moving on to looking at algorithms today, a very, very important topic in this course. We're looking at algorithms which crop up in maths, they crop up in computing, and it may be a term that's unfamiliar to you, so let's just define it. There's a few ways to define it really, but the key point I want to get across is that an algorithm is a set of ordered instructions which solve a problem. That's sort of a key bit. They consist of instructions, so it could be code, it could be something written, like a recipe is an algorithm, an instruction manual is an algorithm. Your end result is you get a cake, or you build a piece of furniture. You also get algorithms, of course, in software on the internet. So an example I can think of on YouTube, you have all these related videos, and YouTube has an algorithm that finds these videos for you. It looks at your history, it looks at what you might be into, and it shows related videos on the side. And obviously Google has them to display search results, and what they all share in common, they're all ordered instructions and they solve a problem. They have an end result, and that's why often they're likened to functions. Functions in code they're like a little packet of code which give you an end result. It could be a number, it could be just a task that's done. And all these algorithms they share three things. They're precise, they're well defined, and they are finite. So let's just have a look at these in a bit more detail. When I talk about precision, what I'm talking about, we're looking at the fact that we get an answer back. Our problem is solved. So precision, we're looking at the fact that we actually get accurate answers. Our problem is solved. However, you've got to be slightly careful. You've got to look at it in terms of efficiency. Right, so we're looking at it in terms of efficiency, but more specifically, we're looking at it in terms of time efficiency. You don't want an algorithm that takes forever. For example, if your algorithm in your sat-nav, perhaps, so it finds you the quickest route to get somewhere, and there's billions of combinations, you don't want it to take a day to find a route for you. You want it to take a minute or so, and that's why algorithms are built with time efficiency. They're designed so that they are as quick as possible, and if that means that you lose some precision, your answer isn't as exact as you want, then that's okay, because it's not wasting your time. Every time you Google something, you don't want the algorithm to take 10 minutes to find the list of results. I mean, you may get results that are more precise to you, but you're not going to wait 10 minutes. You want to wait half a second or however long it takes. So that's quite important. We talk about time efficiency in terms of algorithms, but also precision. Okay, so we also want algorithms to be well defined, and this means that they have a set input or inputs and set outputs. So inputs slash outputs, and we'll also write this as I/O in case you see that notation. And I can think of a couple of examples. So first of all, if we perhaps look at an example, if we have two inputs, 2 and 8, and we have an output of 16, what we can see the algorithm has just multiplied them together. That's quite simple. You can see 2 and 8 times together is 16. That's what the algorithm's done. It gets slightly more complex when we have e.g., so if our input is 16 and our output is 4 and minus 4, you may realize that what we're doing here, we're doing the square root of 16. And what that means is we've got two outputs, because the square root of 16 can be 4 times 4 is 16, but also minus 4. Minus 4 squared is also 16. So we get two outputs in this case, but usually it would have one output but several inputs perhaps, or maybe even no inputs. You can have a null input where you get nothing inputted, but you have an output too, like a random number could be an example of a null input. Okay, moving on to looking at what we're talking about when we say finite. Hopefully it's the simplest of the three, but we just want it to not last forever, so it's not going to be an infinite loop. There'll be a point where the algorithm cuts off. If it can't find an answer, it'll stop itself. It's not going to go on forever and waste your time, because that would just cause a runtime error, but we'll look at errors in another video. So usually algorithms are executed by a computer, but when you're planning them down, so we usually show algorithms in two ways, first of which is pseudocode, and the second of which is flow diagrams or flowcharts, same thing. So first of all, let's look at what pseudocode is. It's probably a good time to mention pseudocode. You'll probably use it in your controlled assessments perhaps, or you'll have the option to, and in your exam they may ask you to express something, an algorithm in pseudocode or flow diagram, or either. So it's up to you which one you use, but what pseudocode is, it's basically a high-level informal description of code. So when we talk about high-level programming languages, we'll look at this in the next video, I think, or yeah, the next video. But what it means is just mainly written English, because it's designed for humans to read. A computer will never run in pseudocode because it just doesn't make sense. And this is an example of pseudocode. This code's doing, it's basically adding up all the values in a list. And if we actually did this in Python, if this was our plan and we put it into code, it would look like this. So basically, pseudocode is sort of up to you. It's for planning. It doesn't actually matter what you write in it. It's, like I said, it's almost completely written English. But there's a few conventions I would advise you stick to. I've always, when I assign something, a list or a variable, I always do this little arrow. That's just something I've done, but I don't think you need to. You could do equals. You could just write list is this, or yeah, is instead. And then for loops and functions and procedures, I always do, so if I'm setting a for loop here, I'll do end for at the end. That's just a convention I've got used to doing, but pseudocode is sort of up to you. As long as it can be read and interpreted quite easily, then it doesn't really matter. So the second way is with flow diagrams, and flow diagrams are pictorial representations of code. So it's basically just like a visual version of pseudocode, and this suits some people more than others. They're usually less detailed, but it doesn't mean you will lose marks. It might be easier for some people to do. I've always preferred using pseudocode, but that may be different for other people. So basically, I'd recommend you use a mix of 4 blocks of flow diagram. And I mentioned these terms: sequence, selection, and iteration. These are 3 different types of program flow control, which we'll look at in a few videos' time. So first of all, you have the start block, and this denotes the start of your program or the start of an algorithm, and it has only one output. It has no inputs. Yeah, I mean, if you're doing an algorithm with an input, you do another block below it. You'd have a process block, which is here. So decision block is the selection stage for selection block, but like I say, I'll talk about that in more detail in a couple of videos' time. And it makes a Boolean choice. It has 1 input and 2 outputs. And a process block represents an operation carried out, such as what the algorithm actually does, and it has an input and an output. And so the process would be the start of your algorithm, but not the start of the actual flow diagram. And then you also have the end, which just wraps up quite nicely, and it's the opposite of the start symbol, has 1 input and 0 outputs. So that's it for today's video. I'm trying to make it as quick as possible. We're looking at programming languages in the next one, so hopefully it was useful, and I'll see you in the next video. Thank you.